Now, you might be asking yourself, hey, cool, Patrick, but why are we talking about this storage thing? Yeah, this is really interesting to know, but I thought we were trying to optimize gas-wise. The reason that we're talking about storage is because reading and writing from storage is an incredibly expensive operation. Anytime we do it, we spend a lot of gas. Remember how before when I said when you compile your code, it gets compiled down to this weird bytecode? Let's go back to Remix. Let's hit compile. Let's go to compilation details. Go to Remix, then we select bytecode and we scroll down a little bit all the way to the bottom. We'll see this thing called opcodes and object. The object is the contract in pure bytecode, and these opcodes are the bytecode converted to something called opcodes. These are the low-level computer assembly-level instructions that are actually executing and actually doing what our smart contract should do. And guess what? Each one of these incredibly low-level codes has a specific gas cost associated with it. If we go to evm.codes, this is a website that actually keeps track of a lot of these opcodes gas costs. And right on the left-hand side, we can see the opcode in its bytecode format, and then the name of the opcode, and then the minimum amount of gas it actually spends to do that opcode. So anytime you add two numbers, it costs 3 gas. Multiplying costs 5 gas. Dividing 5 gas, so on and so forth. And if we keep scrolling, we're seeing a lot of 3s, a lot of 2s, a couple of 100s, some 20s. We get down to here. Oh my goodness. S-load and S-store are both 100. That's way more expensive than a lot of these other ones that we're seeing, which are like 2 or 3 or 5. S-load is the opcode that loads a word from storage. Anytime you read from storage, you're spending a minimum of 100 gas. S-store is the opcode that stores a value in storage. Save a word to storage, which also costs a minimum 100 gas. If we look just up above that, we actually see M-load and M-store, which stand for memory load and memory store. If we load or read from memory, it only costs 3 gas. So it's almost 33 times more expensive to read and write to storage than read and write to memory. So a really easy gas optimization we could do is we can read and write from memory way more than we should be read and writing from storage. So with this in mind, if we come back to our Foundry withdraw function, we look in here, are we reading and writing to storage a lot in here? Oh my goodness. Let's look at this loop here. So we're saying uint256 funder equals 0. Okay, sure, whatever. Funder index is greater than s_funders dot length. The length of the funders array is stored in storage. So every time we loop through this for loop, we're rereading from storage. Let's create a new function called cheaper withdraw. This will be public only owner as well. Let's keep this memory to storage gas optimization piece in mind, and let's rewrite this function so that we're reading and writing from storage a lot less. So first off, instead of reading from storage every single time, we could say uint256 funders length equals sfunders.length. That way we'll only read it from storage one time, and then every time we loop through, we'll only read it one more time. And this is why this syntax of adding this s underscore here is really good. Anytime you see this s underscore, your brain should go, oh my goodness, I'm actually reading from storage. Maybe I should consider not doing that and reading from memory instead. So we're going to read from storage once here. And for our for loop, we're going to say for, do the same thing. uint256 funder index equals 0. Funder index is less than funder's length, which is now a memory variable instead of a storage variable. And then funder index plus plus. Okay, cool. Now, okay, in the withdraw function, what do we do? Okay, we get the funder address from storage. There's really not a great way around this. We pretty much have to read from storage every single time here. So let's go ahead and stick that in here. And then we do this mapping. There's really not another way around this. So we're just going to stick this in here as well. We still need to reset the storage, so we'll do that. And there's not a whole lot much to do in here, so we'll just do this as well. So we now have this cheaper withdraw function that we're going to loop through this array, reading the length from memory as opposed to reading the length from storage over and over again. So now that we have this cheaper withdraw function, let's go back to our fundme test.sol. Let's scroll down, and we have this test multiple withdraw funders. I'm actually just going to copy paste this whole thing, which wouldn't be good practice in an actual test file, but for us, we're going to do it. I'm going to paste it. I'm going to call this test withdraw from multiple funders cheaper. And instead of calling withdraw, we're going to call cheaper withdraw. And that's it. That's the only difference that we're going to do. Now, let's pull up our terminal and we'll run forge snapshot. So now we should create a gas snapshot with all of our tests, but will we have test withdraw from multiple funders and test withdraw from multiple funders cheaper. And if we go to our gas snapshot, go to the bottom, we see test withdraw from multiple funders, 987,915 gas. Test withdraw multiple funders cheaper, 987,136. We're saving almost 800 gas by using this cheaper, less storage intensive reads for running our contract. Amazing. This is fantastic. We've learned so much and we only have a couple more things to do for this lesson. And then we're going to push this code up to GitHub and have your first project, which is incredibly exciting. So I fumbled this a little bit. I didn't really talk about it too much, but I did update some of the errors and I updated some of the variables without explaining it too much. Immutable variables, again, these are not stored in storage. So it's good to have some identifier to say that A, they're unchangeable, and B, they're actually not in storage. So I go by the Chainlink style guide, which does this I underscore for immutable variables and uppercase for constant variables. Having style guides is really important and gets more important the more advanced you get because it makes your code much more readable and you look like a more advanced developer. So immutables have I underscore, storage variables have S underscore, and we just explained why that's so important to know what storage variables actually are. A lot of people use the Solidity visual developer, which also automatically points out storage variables for them as well. I don't really like to use it though, because I feel like it clutters up my user experience a little bit. But if you're having a hard time identifying storage variables, maybe that's an extension for you. The Solidity docs actually have an entire style guide as to what to do for code layout, function names, line length, and all this other stuff. So I've already updated these to iowner, sPriceFeed. We've added some getters at the bottom. There's a couple of more style guide things for us to do, but we'll do that in later sections of the course. I subscribe to the Chainlink Solidity style guide, which I've left a link in the GitHub repo associated with this course, which talks about everything that we went over here. We want to keep everything private, use S underscore, use I for immutables, S for storage variables, etc. And you can read this if you want. Style guides seem like they're a little bit bored, but the more you code, the more you'll realize how they make your life way easier.